The research paper delves into the characterization of multiplicative asterisk operator Jordan-type maps on alternative algebras, a significant area of study in understanding the structure of these non-associative structures. Building upon previous works on associative structures and their extensions, the authors emphasize the importance of these maps in comprehending the intricate nature of alternative algebras. They define and explore the properties of multiplicative asterisk operator Jordan-type maps, highlighting their relationship to asterisk operator Jordan and asterisk operator Lie products. The paper also discusses the sequence of polynomials introduced in 4, which serves as a foundation for the characterization of these maps. The author's main result is centered around the application of these maps on alternative W asterisk operator factor, providing a new perspective on the structure of these algebras. This research contributes to the ongoing exploration of non-associative structures, shedding light on the complexities and nuances of alternative algebras. Throughout the paper, the authors maintain a technical and professional tone, utilizing precise language and domain-specific terminology to convey their findings. This work is essential for researchers seeking to advance our understanding of alternative algebras and their role in various mathematical disciplines. Here is a refined version of the transcript, condensed to 250,350 words. This research paper presents a novel approach to a specific area of research, leveraging key methodology or concept to investigate research question or objective. The authors employ specific technique or algorithm to analyze dataset or study population, yielding insights into specific phenomenon or relationship. A crucial aspect of this study is the development of novel concept or framework, which enables the integration of previously disparate concepts or data types. This framework is underpinned by mathematical equation or algorithm, which facilitates the quantification of specific variable or effect. The results of this study reveal key finding or trend, which has significant implications for specific field or application. Notably, the authors observe unexpected or counterintuitive result, which challenges prevailing assumptions in the field. The authors validate their approach through specific evaluation metric or statistical test, demonstrating the robustness and accuracy of their methodology. Furthermore, they discuss the limitations of their study, including acknowledged limitations or assumptions, and highlight avenues for future research. This work builds upon previous research in specific area, extending specific concept or methodology to new context or application. By doing so, the authors provide a nuanced understanding of research question or phenomenon, shedding light on the complex interplay between specific variables or factors. The significance of this study lies in its ability to specific contribution or impact, with potential applications in specific field or industry. As such, this research contributes to the ongoing development of broader research area, informing strategies for specific goal or objective. A main theorem is presented, establishing a connection between two alternative asterisk operator algebras, A and A, with identities Ia and 1A, respectively. This theorem states that if A satisfies the condition, spade suit, where x, ai, equals 0, implies x equals 0, and there exists a bijective unital map phi from A to A, preserving certain quadratic expressions involving idempotents E1 and E2, then phi is asterisk operator additive. This result has significant implications for prime alternative asterisk operator algebras over ground fields of characteristic different from 2 and 3. The proof of this theorem relies on several lemmas. The first lemma shows that phi 0 equals 0, utilizing the surjectivity of phi and the given condition on quadratic expressions. The second lemma demonstrates that for any A11 element of A11 and B22 element of A22, phi A11 plus B22 equals phi A11 plus phi B22, leveraging the surjectivity of phi and the properties of quadratic expressions. The third lemma establishes that for any A12 element of A12 and B21 element of A21, phi A12 plus B21 equals phi A12 plus phi B21, again utilizing the surjectivity of phi and the quadratic expressions. These lemmas collectively contribute to the proof of the main theorem, implying that the map phi is asterisk operator additive. This result has significant implications for understanding the structure and properties of alternative asterisk operator algebras and their transformations, providing insights into the relationship between these algebraic structures and their transformations. The application of proposition 1.2 and lemma 2.3 further develops the properties of the function phi. Starting with the surjectivity of phi, it is shown that given phi, A12, plus phi, B21, element of A, there exists T element of A such that phi, T, equals phi, A12, plus phi, B21. The injectivity of phi then deduces that T11 equals T22 equals 0. The analysis proceeds by examining the behavior of Qn asterisk operator, E2, T, C12, and its relation to Qn asterisk operator, E2, A12, C12, and Qn asterisk operator, E2, B21, C12, highlighting the properties of elements in A12. The proof of lemma 2.4 is also outlined, establishing the additive properties of phi on elements of A11, A12, A21, and A22. This section's technical details and mathematical derivations are critical to understanding the paper's core contributions. We initiate our analysis by leveraging the injectivity of phi to derive several equalities. Specifically, we have Qn asterisk operator, E2, T, equals Qn asterisk operator, E2, B12, plus Qn asterisk operator, E2, C21, which yields 2T22 plus T12 plus T21 equals B12 plus C21. This implies T22 equals 0, T12 equals B12, and T21 equals C21. Next, we observe that Qn asterisk operator, 1a, E1 E2, B12, equals Qn asterisk operator, 1a, E1 E2, C21, equals 0, and using proposition 1.2, we obtain phi, Qn asterisk operator, 1a, E1 E2, T, equals phi, Qn asterisk operator, 1a, E1 E2, A11. By injectivity of phi, we have Qn asterisk operator, 1a, E1 E2, T, equals Qn asterisk operator, 1a, E1 E2, A11, which yields 2T11 2T22 equals 2A11, implying T11 equals A11. We then proceed to prove lemma 2.5, which states that for any A11 element of A11, B12 element of A12, C21 element of A21, and D22 element of A22, we have phi, A11 plus B12 plus C21 plus D22, equals phi, A11, plus phi, B12, plus phi, C21, plus phi, D22. To prove this, we use the surjectivity of phi to find T element of A such that phi, T, equals phi, A11, plus phi, B12, plus phi, C21, plus phi, D22, with T equals T11 plus T12 plus T21 plus T22. We then apply proposition 1.2 and lemma 2.4 to obtain phi, Qn asterisk operator, E1, T, equals phi, Qn asterisk operator, E1, A11, plus phi, Qn asterisk operator, E1, B12, plus phi, Qn asterisk operator, E1, C21, plus phi, Qn asterisk operator, E1, D22. By injectivity of phi, we have Qn asterisk operator, E1, T, equals Qn asterisk operator, E1, A11, plus Qn asterisk operator, E1, B12, plus Qn asterisk operator, E1, C21, which yields 2t11 plus t12 plus t21 equals 2a11 plus b12 plus c21. This implies t11 equals a11, t12 equals b12, and t21 equals c21. Similarly, using qn asterisk operator, e2, t, we obtained 2t22 plus t12 plus t21 equals 2d22 plus b12 plus c21, which implies t22 equals d22. Finally, we prove lemma 2.6, which states that for every a12, b12 element of a12 and c21, d21 element of a21, we have phi a12 b12 plus a asterisk operator 12 equals phi a12 b12 plus phi a asterisk operator 12 and phi c21 d21 plus c asterisk operator 21 equals phi c21 d21 plus phi c asterisk operator 21. This concludes the summary of page 5. This section of the research paper presents a series of lemmas that elucidate the properties of a homomorphism, specifically the linearity and surjectivity of the function phi. These lemmas are pivotal in establishing the main theorem of the paper, which can be inferred as a consequence of these results. The first lemma, lemma 2.6, demonstrates that for all A12, B12 in A12, the homomorphism phi preserves addition. This is achieved by showing that the sum of two elements in A12, when mapped through the homomorphism, equals the sum of their individual mappings. This result is crucial for demonstrating the linearity of phi. The second lemma, lemma 2.7, extends the previous result to include elements from different sets I. 1 is less than or equal to I does not equal j is less than or equal to 2. It shows that the homomorphism phi also preserves addition for elements across different sets, further reinforcing the linearity of the function. Finally, lemma 2.8 focuses on the diagonal elements of the matrix, proving that the homomorphism phi is surjective. This means that for any element in the image of phi, there exists a preimage in the domain of phi. The proof involves using the previous lemmas and the injectivity of phi to establish this property. In summary, this section provides a detailed analysis of the homomorphism phi, demonstrating its linearity and surjectivity. These properties are fundamental in understanding the behavior of the function and its implications for the main theorem of the paper. This refinement maintains the technical accuracy and depth of the original content, condensing it into a direct and concise form suitable for voiceover narration. The focus is on the preservation of asterisk operator addition and asterisk operator multiplication under a bijective unital map between two alternative asterisk operator algebras. The key result is that if the map satisfies certain conditions, it is a asterisk operator ring isomorphism. The conditions include the preservation of asterisk operator addition and asterisk operator multiplication, as well as the preservation of idempotent elements and specific subsets. The main theorem states that if the asterisk operator algebras satisfy certain conditions and the map preserves asterisk operator addition and asterisk operator multiplication, then the map is a asterisk operator ring isomorphism. This includes the preservation of the asterisk operator operation, which is essential for maintaining the algebraic properties of the original algebra. The lemmas presented on page 8 establish the properties of the homomorphism phi between alternative algebras. Specifically, lemma 2.10 proves that for x element of I, with I does not equal j, phi x element of I, utilizing the definition of phi and the flexibility property of alternative algebras. This property is then used in lemmas 2.11 and 2.13 to demonstrate the additivity and multiplicativity of phi, respectively. Additionally, lemmas 2.12 and 2.14 further illustrate the multiplicativity of phi, collectively establishing this crucial property in the study of alternative algebras. The proof of the additive property of the map phi continues, demonstrating that phi ib equals phi aij phi bij for aij bij element of I with I does not equal j. This is achieved by applying lemma 2.10 and the additivity of phi, as established in lemma 2.15. Consequently, phi ab equals phi a phi b implying that phi is a asterisk operator ring isomorphism. The application section introduces alternative C** operator algebras, non-associative generalizations of C** operator algebras that appear in various areas of mathematics. These algebras are characterized by the condition AB equals of B for all elements. A element of A alternative W** operator algebras are defined as dual Banach spaces, and prime alternative W** operator algebras are referred to as alternative W** operator factors. Notably, non-zero alternative W** operator algebras are unital. Theorem 3.1 establishes that if a map phi between two alternative W** operator factors satisfies a certain condition involving the Qn** operator product, then phi is an additive asterisk operator ring isomorphism. Corollary 3.1 follows, stating that under these conditions, phi is a nonlinear asterisk operator Jordan-type map if and only if it is an additive asterisk operator ring isomorphism. The research paper discusses the concept of Jordan triple maps and their properties in alternative rings, highlighting their importance in the context of non-associative algebras. It emphasizes the significance of the Vadov-Palmer and Gelfand-Naimark theorems, as well as the role of idempotent elements. The authors reference various works, including those by Ferreira, Guzzo Jr., Garcia, Palacios, Hentzel, Kleinfeld, Smith, Taghavi, Nouri, Razagi, and Darvish, to provide a comprehensive understanding of Jordan triple maps and their applications in physics, particularly quantum mechanics and quantum field theory.